I'll do review questions today. And after we're done with the review questions here, we'll start our next chapter. Okay, it's thermal equilibrium. A chapter, it's very small topics, multiple small topics all together. So you have a revisit of thermometer, you have a revisit of specific heat capacity, exact same thing, nothing new. So that's actually a good thing because this is actually exactly the same. So in fact, if you look at what thermometers are, you'll notice that it's a pointless topic. When I'll be doing this, it will be 5 minutes. That's it. That's the whole chapter, whatever you see here. Okay, so it's like, what are the different types of thermometers out there? What are the different scales? And how do you convert from degrees Celsius to Kelvin? Okay, literally that. If you see here, it's just that conversion. Thermometers are made on different properties. What are the different properties out there? Like density, gas, pressure, resistance. That's it. Okay, and absolute zero is the lowest temperature attainable. Okay, so yeah, this one is just I think they're assuming that it's been 2 years since you did thermometers, right? So it is just a recap remote on Arkichuna. Dorkar ki, has it? Why do you learn this? So they don't ask questions, so I'm not really sure why do they even teach this. So it's no question I can take it. The only thing that you can actually make use of is the one I have given here in red. Always convert degrees Celsius to Kelvin for all maths. That's it. Okay, Arkichuna. Yeah, so this is a revisit of all those chapters. All those chapters when O levels, all those small chapters. Once again, remember gas laws. Your PV equals to So PV equals to energy to chemistry te shikho tomra. On physics will derive that. How do we get that form? Okay, so yeah, it'll come full circle. Literally, you figure out where did all these equations come from, why do they even exist, and everything. Okay, so then the next chapter, okay. So last class we did a topic called escape velocity, and I think I told you it's an interesting topic. They give you derivations based on this, questions based on this. So what's escape velocity? So escape velocity is the velocity with which you need to throw something, right? So that it escapes the Earth's gravitational pull. So let's try one by one. Okay, let's throw this object at 10 meters per second. What would this object do? So as you learn from your AS, it will keep going up. It'll decelerate. I'll keep decelerating, and it'll stop. And then what will it do? Fall back again, because it did not have enough energy to go far enough to escape the Earth's gravity. Okay, so our plan here is to give it so much velocity that it'll go so far that the Earth's gravity would become what there? Zero, right? And then it shouldn't come back. And that's escape velocity. So how do we do that? So trial and error is one way, obviously, but the math makes it easy for us. We did the math, and math ki slow. We assume that when you throw an object all the way up to infinite, right, the change in GP would be whatever GP is here to whatever GP is there. Wouldn't that be the gain that you need? Now, what's the GP of an object at infinite? Zero. And what's the GP of an object on the surface of the Earth? The GM by radius of Earth, that equation, the potential, right? So using this value of GP here and zero there, we can find a difference here. Now, this is the gain in GP you need. And it turns out all the K would be converted to GP, right? So can't I write this, that the GP gain must be equal to all the K lost? And the GP that I'm trying to find here is to go from where? Surface of the Earth to infinite, right? So we do that small math here to figure out how I said it. I hope you know by now how to do this math. We don't find GP. What do we find? Potential. We find potential at different places. Okay, we find different potentials. So we found the potential at this place. We found the potential at that place, and we found the change in potential. And change in potential ke kichu de multiply korle you get GP. What is it? Mass. Okay, so that equation is very underrated, but খুবই important. I mean, that equation this one. Okay, that gravitational potential is equal to gravitational potential energy divided by mass. So we learn how to find potential in our syllabus. We do not learn how to find potential energy. So once we find the potential and we find the potential difference in everything, all you need to do is just multiply mass with that potential, and that will give you the value of what? GP. Is there a formula for directly finding GP using the equations we have? Yes. I don't know why they removed it. It was there. Okay, 2011 পর্যন্ত ছিল, but they got rid of it. And some students actually derive it. I've seen students, they'll come and tell me, I found this formula. Does it work? And it actually works. I'll show you what that formula is. what is the formula for GP instead of potential? MGH na, so change in GP, or not change, the actual GP. So what is the GP of this calculator or this remote right now? Not potential, okay? I want to find the actual value of the gravitational potential energy here. And when I find the gravitational potential energy here, I'm finding it from which point? No, center of the Earth, on a unit. So Charlie will go all the way to the center of the Earth, right? So how do I find this value? So typically we used to use this formula MGH, and we learned that this formula is not valid anymore for large distances. Why? Because what changes at large distances? Yeah, G changes, right? So we can't use this. Now, এখান থেকে derive করা possible from here. I'll show you how. So we know that GP is what? Phi into M, right? And what is phi? Minus GM by R times M, right? So from here, what is the formula? Minus GMM by R. This is actually the true formula. Okay, and it they can show math, but they don't allow it. So if you do this, if you answer your question using this equation, right, you'll lose M marks. But your method marks, okay, there are marks in your mark scheme. Method mark will be lost. Okay, so what is the only acceptable way of finding gravitational potential energy in your syllabus? Yeah, you first find potentials, then you find potential differences, then you multiply potential difference with what? Mass. Okay, that's the only way. I've given the step-by-step process here. AJ. No, method marks cut it. Because the problem is that there are a lot of questions in O levels, for example, right, of motion. You could have done it using kinematics and differentiation and integration, right? Are you wrong? No, but method mark is enough. Okay, so it's a little unfortunate, but they are strict about it. So yeah, this is the process. So you first find the potential at 2 points, then you find the change in potential, and then you multiply the change in potential with what? Mass. Okay. So yeah, that's escape velocity. So on our math paper, we found that the escape velocity was what for Earth? 11.2 kilometer per second. So it means that if I take this marker right now and throw it up into the air at 11.2 kilometer per second, right? It will leave the Earth's gravity and never come back, ever, right? But then we discussed and we found that that's not realistic, because as you throw it at such a high velocity, what would be extremely high? Air resistance, right? And it'll barely make it to the top of the atmosphere, top of the stratosphere, ionosphere, exosphere, and space, right? But it wouldn't make it to atmosphere, right? Why is that so? All the energy K will be used to do work against what? Air resistance. It'll melt clearly, so it'll not make its way out. But yes, on Moon, on other planets that don't have an atmosphere, you can actually use escape velocity to launch. There's nothing wrong in the concept. Right, so one last thing before we move on. It is the graph. It is graph easy because there's only one graph here. So this is gravitational potential graph. Okay, Tatiguri, I want to do the review question, so let's see what this is. How does a graph of gravitational potential look like? So for that, we only have one graph out there, because there are no other variations possible. This is the graph. Now, what I want you to do is, I want to make you apply your knowledge of math to come up with the graph, because I don't want you to always memorize all the graphs. It is not really a fruitful approach. Okay, there's so many graphs out there. Let's try to do it out. Let's try to explore and find out the graph. Is the first graph of our A2? Is this the first graph? No, it's not the first graph. I think this is the third graph. Yeah. So what is the axis here? So this is phi, which is joule per kilogram, and this is distance. Okay, and we want to find the variation for gravitational potential outside the mass, because I think I told you before that we are not bothered about inside the mass because it's not an attainable thing to begin with, and also we assume our masses to be point masses. Okay. So there is this strange way of approach. Let me explain, okay? Imagine this box here, and then the center of mass of this box is where? In the mathematical center, like diagonals draw where you can find the center. That's what the center of mass is, right? And we assume in our math, right, this box to be what? A point, right? But it has a catch though. You will not be able to get to the point, cannot, because what will you always hit before you reach there? The surface. You get my point? So whenever we have our question, right, we assume the mass of a planet to be at the center, but as you start to get closer to the center, there's a barrier. At one point, you can't go any further in. What is that barrier? The surface. So all our graphs, right, start from where of a planet? Surface, radius of Earth, right? But where does all the mass exist though? At the center. Do you get my point? Because eventually there's no way you can break through this and get to the center. So that's the limit. So if I draw this graph here that I've shown you right now, that dotted line that you see, this dotted line, right? This represents the maximum distance you can get close to a planet. And that distance that you see here is how much? Radius of the Earth, right? So the radius of the Earth. Now the thing is, how does the value or how does the graph look like? So I'll give you an equation. I want to see, can you come up with graphs from equation? Okay, it solves half of your problems. So phi is equal to minus g m by d. That's the formula, and I want you to plot the graph for this. Okay, so how to plot the graph? I'll be teaching you math here right now, not physics. Okay, how to come up with the graph equation. And I personally feel like you should be better at this than I am because you have this in your syllabus. Do you have like drawing any graphs out there? In what? Statistics. No, statistics na. তোমাদের P1 P2 তে কি graphs থাকে? So do you know how to translate graphs? Like if I put like a minus in front of a graph, what does it mean? If I put a minus in front of the y-axis, what it means, right? Reflection along the y-axis, reflection along the x-axis. If I put the minus within the bracket, it's a translation forwards, plus a translation backwards. These right? That's it. That's what I'm looking for, okay? So if this graph were to be in terms of y, it is actually y equal to minus 1 by x. So that's the graph I'm looking for. So does anyone know what would the graph look like here? So I'll teach you, don't worry. Is if you can solve this, it'll solve a lot of problems in the future as well. So this is my y-axis and this is my x-axis. Let's first learn the graph for 1 by x. Okay, that's how we'll do it. We can't directly get here. Okay, that would be in the right way. So what's the graph for 1 by x? Yes, so by now I hope দেখলাম না, but কেউ যদি এটা না show করে থাকো, okay, that's wrong. That's not the answer. This is what actually y equals to minus mx plus c. Completely different physics and math. They're two completely different things. Okay, so this is not the graph I'm looking for. I'm looking for 1 by x, and 1 by x is called the inverse graph, right? So inverse মানে হচ্ছে if one increases, the other decreases by what factor? Exponential factor. Okay, and I think by now A2 you should know this word. Do you know what an asymptote is? Yeah, so now you know that this line is an asymptote, this line is an asymptote, which means that you will never be able to touch that line, but you'll go very close to it. And in infinite, you will touch the line. That's the thing, because as it tends towards infinite, value tends towards zero. So you'll eventually touch it. Not here. I can't really show it here. Okay, but very far distances, it'll be so close, right? You can assume it to be touching the axis, right? Anyways, this is the graph for 1 by x. If I put a minus in front of it, right? What does it do? Yeah, it reflects along the x-axis, right? So you graph jeta hobe, this is my minus y. The graph will reflect along the x-axis, so it's like a mirror, and it'll become that. Do you agree? Right. So this is our graph. This is the answer. আমাদের হচ্ছে minus gm by d মধ্যে. Why is this the graph? I'll tell you. I'm drawing the graph for phi versus d, where g and m are what? Constants, right? So if I did like an equation here, it'll be k by x, and the k would be a constant. And yeah, that's about it. So for every distance, the value of your phi decreases, right? So I'm going to draw for that. Okay. So this is my minus phi. And as you know that all the values of phi will always be what for these graphs? Negative. Can you tell me why? 3 marks এর জন্য ছিল। Losing which energy? Yes. So that's why loss is indicated by negative, right? And one more reason. Yeah, we are considering infinite to be 0. So once you move below that point, all the numbers are negative below that point. All the numbers are positive above the 0. We never go to that point. So the maximum is at infinite, but the value is 0, right? Anyways, so if I plot the graph here, the graph that you get is like this. Now, a graph structure is very easy to remember. Students will memorize this, but what does a graph help us attain is something important. So this is your graph, right? And this line that you see here, it's the surface. So can I reach the surface? No. But at the surface, will I become an asymptote or will I meet? Yeah, I'll meet, right? And then I meet at a point that is a maximum potential energy. What is that going to be? Minus Gm divided by Re. Yeah. Okay. So that's the value. And as you keep going further away, you can see that the gradient of the graph is gradientless, right? Value of the graph is decreasing or increasing. As you go further away, what are the values becoming? Increasing or decreasing? Increasing. Okay, negative value সাথে যেটা কাজ করে, and lower value is higher quantity, right? Minus 10 and minus 200. Which one is bigger? Yeah. So wait, what? Minus 10 or minus 200, which is a bigger number? Sure. Okay, that's okay. So yeah, this is minus 200, this is minus 10. So obviously, the further you go, the greater the energy you have, right? So the thing that you should be careful about is this, the gradient of the graph. So the gradient of this graph, is it positive or negative? Positive. Acha. It is positive. Okay. Now, the thing is, this gradient will provide us with gravitational field strength. How? Look at this. What's gravitational field strength? G. G is the statement negative gradient of a potential versus distance graph. Right? Because as you go very close to the center of the Earth of massive project. So look at this. There'll be multiple places we'll like see this. This is here once. Our chapter in the charges chapter. Okay. So G is a negative gradient of potential versus distance graph. So let's see, what does that even mean? So if I take the negative gradient here, let's do a bit of math. Okay. If I take the negative gradient here, what should that be? So gradient is equal to minus d phi by d that. Do you agree? Gradient is change in phi by change in d. Now, what is phi going to be here? Minus g m by d divided by what is the change at the bottom? D. So if I put them together, what do I get? Minus gm by d square. Do you recall what that is? Yeah, that's small g. Okay, so that's where you get the value from. So if you ever want to find out the gravitational field strength of a planet from a potential graph, right, what will you do? You'll find the gradient, but what of the gradient? Negative of the gradient. And it makes sense. I'll explain why it makes sense, okay? Can anyone predict what should this gradient be? Make a tangent draw. What is the gradient of this line? Yes, 9.81. Because I'm where on the planet right now? Surface, right? So if you actually had a proper graph with numbers in it and you found the gradient at that point, right, you would find it's 9.81. And as you go further and further over, obviously the gravitational field strength is decreasing, and that's evident from the graph because the gradient of the graph is what? Decreasing. Is that okay? So yeah, that's all we have from this graph. There is a term used to describe this graph. It's called the gravitational well. So what's a gravitational well? So do you know what a well is? Like, well in which there's water in it, right? So why do they call it gravitational well? Because I think it's just general knowledge, extra information. It's to do with the formation of a black hole. So black hole is a well, right? Our sun is a well, the earth is a well. These are all gravitational wells, right? But the difference is the sun is a well, and that well is not a bottomless well. Do you understand what I mean? So there's actually an end to it. The earth is a well that has an end to it, right? A black hole is a well that has what? No end to it. Okay, so that's why you keep falling in a black hole perpetually. You never stop. So, if somebody falls into a black hole, right? For how long does he fall? Eternity. There's no end to it. It will keep falling forever and ever and ever because there's no end to it. Okay. What? Oh, that's a speculation. I mean, no one has proof for it, but yes.
That is just a very dense
very dense point. Yeah.
It still has a radius.
Yeah. So there are very big black holes, but the radius is not the black hole's radius. It's the accretion disk. There's a disk, the event horizon, the size of that can vary. But the end of the black hole, there's no big black hole, small black hole in terms of the point of singularity that makes the black hole. But the opening of the well can vary, right? So you can have a well that's that big, and at the bottom of that well, what do you have? The black hole. Or you could have a well that's that big, like that. But what's at the bottom again? The black hole. Yes. So there are black holes that are bigger than our solar system, the event horizon. But the singularity, the point where everyone's trying to get to eventually, is the same for all of them. It's just a point. It's singularity. Okay. So yeah, it's like a well. And the thing is that a well, this concept of the well. So the concept of the well actually came from the graph itself. So imagine I'm on the other side of the planet, right? Wouldn't my graph look like this, Taleb? Again, if I drew the graph for on the other side of the planet, wouldn't it be a mirror like that? And if you look at the graph, what does it look like? It's like a well, right? And for a black hole, you can actually get very close to what? Yeah, so that means that well is like a, abyss, no end to it at the bottom. Okay, so anyways, just letting you know, because you'll find this term used like in a lot of places, the gravitational well. It comes from this concept. Okay, so that's your graph. I will add a couple of notes here, and then we'll start the review questions. And if you have any questions, do let me know. You can. It takes infinitely long. That's the problem. So if you do your math, it'll say you'll reach it there. They'll give you like a timeline.
Why does it take so long? Is the gravity really strong so you go faster?
No, it's your time dilates. So there's something called time dilation. So if you have seen the Interstellar movie, you'll probably have heard of it. Like if you're very close to a very strong gravitational field, time for you runs very slow. Others it's fast, right? So in a black hole, your time stops. So if your time stops, right, like your clock is not ticking. So you want to get to somewhere, and they said you'll take 2 seconds to get there, but the clock is not moving. So how long will it take you to get there? So it doesn't say stop; it says trying to move. So it gives you hope that it will one day get there, but it never moves. Depends on what kind of mass became a black hole. So we had this in our O levels, that this event called a supernova, where the star collapses upon itself, and how big the star was that collapsed results in the size of the black hole it forms. So if it's a very massive, like red supergiant, and it collapses, then you have a big black hole. Sometimes smaller stars can also undergo supernova, right? And that'll make a smaller black hole. And what happens is black holes also merge, and they become like a supermassive black hole. That's the one I was talking about. That's like multiple black holes that merge together.
What's the white hole?
It's the other end of the black hole. Yeah. So all the energy has to go somewhere, right? So one of the places the energy goes is the disk. So the disk glows, and that's where the X-rays come out from, and that's how we know black holes exist. So you'll see the famous picture of a black hole is like a red ring, right? That red ring is where the energy is released. But what about all the masses that are absorbed by the black hole? Energy conservation says somewhere the mass should be there, or the energy of the mass should be there, right? It doesn't always amount for the disk energy, so it goes somewhere. The theory is that there's a place where the energy is released, and that's the white hole. It's like a reverse. Okay, it's all on paper in theory. There's absolutely no evidence of it. Yeah, wormhole's genuine.
How do they work? You like always there and you're from the other end.
Yeah, so you enter this door here, if that's a wormhole, right? And you come out from someplace in Mexico, and in between it's like zero time.
And you guys do it?
All right, so gravitational potential. All right, make it fast. We will start solving some questions.
If Germany is you don't want to see the Berlin Cathedral,
Which one?
the Berlin Cathedral, or Berlin Palace, or Paris.
Yeah. No, but I would like to go. But why Germany? Yeah. No, they have castles. Palaces are like things you'll find in Middle East. Yeah. Oh yeah, that's Versailles is palace. Yeah, it's not a castle. It's not. But Germany doesn't have any palaces. These are all castles. Hmm?
The last 12 times.
Last royal family, is that the Nazi? God. We don't know. It's still a mystery. It's a particle called the gravitron, but there's no evidence of it yet. Why would I do like a World War II tour? All the countries that got invaded. Start from Austria, Poland, enter Germany, get defeated at France. Not everything. I mean, this is World War II. Everyone should know about this. It's a war that changed our Earth. Obviously, you have to be if you want to study A levels. Favorite? I only know one of them, so probably that. What others are there? Oh, yeah, Norse. I don't know much about Norse. It's yeah. You guys done? What else? Depends. I have phases. So, when I'm into something, I'm really into it, then I just quit forever. I think Game of Thrones. It's been 10 years. Yeah. It's a bad ending. Which one? Oh, you like the way it ended? No. I mean, it's not the worst ending.
Makes sense, right? Because if the girl would be alive, then she would like kill her.
Yeah. I mean, she. I felt like the whole White Walker part was just unnecessary. I mean, the way they built them up. I mean, for 9 years, it was like they're the ones. Yeah. So that's the only problem.
In the book, there's a third guy.
The books are not over yet, right? Okay, let's move on. Can you go to page number 4 page, review questions, okay? So we'll solve a few questions here. Right, it says that the Earth may be considered to be a uniform sphere of radius that the value here is 6, okay? And its mass is assumed to be concentrated at the center. Given the gravitational field strength of Earth is 9.81, show that the mass of the Earth is 5.99 into 10 to the power 24 kilograms. So you need to find the mass of Earth. Gravitational field strength is provided. So the first thing is that you are provided with field strength, and that is that. You're also provided with the radius, and you need to find the mass, right? So there's only one formula that satisfies the requirement here. What is that? The field strength equation, right? So first equation, like G equals to minus G M divided by D square or R square. That's the gravitational field strength equation, okay? One thing is that the chapter has 4 equations that are very similar, and students get confused too often. I will write them down here just for a recap. So you have F, you have G, you have phi. So these are very similar equations. Can you tell me what is the formula for F? Minus G M divided by D square. And what is the formula for G? Minus G M divided by D square. And phi? Minus G M divided by D. Okay, so these are the 3 equations out there. There are no other equations in your syllabus. Yes, there's one more that you can derive, but it's not officially like an equation. That's the T square 4 pi squared gm by r cubed, the time period one, okay? But that's usually asked to derive in your exam. So yeah, G is 9.81, so I can take minus 9.81 here, equals to minus, what's that capital G? Gravitational, universal gravitational constant. It's the same everywhere at any time, okay? Even at the singularity of a black hole or at the edge of our universe, the value of G is constant, okay? Which is 6.67 into 10 to the power minus 11. And it is one of the reasons why gravitational field is the weakest force out there, because this constant is very small, 10 to the power minus 11, right? If you see Coulomb's law, magnetism, other constants, other power, 10 to the power 7, 10 to the power 8. So if you compare the 2 forces, you'll find that this is extremely weak, okay? Something as big as the Earth can only apply 10 newtons on a 1 kg mass. 10 newtons is just like, that much. So, the Earth, with all its mass, can only apply that much force, which is like really weak, right? So that's why gravitational field is the weakest field out there. Into mass of Earth, we do not know that. We're trying to find that, divided by the distance. So it's a sphere, center of mass, that's the radius. We know the value is 9.81 at the surface. This is radius of the Earth. So there's 6.38 into 10 to the power 6 squared. So yeah, once you do this, you will find the mass of the Earth. No, you can, in this question, you could have just written gm by d squared, no problem, because the minus is just to attribute the fact that the force is attractive. That's it. Okay, there's no mathematical implication here. So yeah, if you do the math, does it show the same number, 5.99? Check for that one. Yeah, so that's the answer. Next is the satellite is placed in a geostationary orbit around the Earth. Can anyone remind me what's a geostationary orbit? Yeah, it's a satellite that spins with the same time period, okay, in the same direction, which means that it remains at the same location above the Earth as the Earth spins, right? So calculate the angular speed of a satellite in its orbit. So calculate the angular speed of the satellite in its orbit. So you need to find the angular speed. Quick reminder, what is the angular speed? Omega, right? And it represents what? No, that's that. But what's the definition in terms of what does it actually represent? Rate of change of angle. How much angle does it cover every second, right? So omega equals to 2 pi by t. That's the equation. So we can use that to get to our answer. They said for this satellite, right? So for this satellite, the 2 pi divided by time period. What should the time period be for the satellite? 24 hours, right? So 24 into 3600. Surprising, it's 3 marks. Acha, it's something to the power minus 3. Acha, minus 7.27 into 10 to the power minus 5. What's the unit? Radian per second, which also they have provided. Otherwise, it's 3 marks. I think the equation has a mark here. Equation at a mark. 24 hectare seconds they convert per hectare. That's probably it. Or maybe the final answer here. Should it be 7.27 or should it be 7.3? Why? But আমরা ওগুলো ইউজ করিনি তো। হ্যাঁ, but standard form এ তো 7.27 ও লেখা যায়। Okay, so you know the right way of writing the answers, and this is very strictly followed in your A2 for all answers, ASL chilo, is that the final answer must maintain the same significant figure as the data provided. And if the data has different significant figure, like, 2, 3, etc., we'll take the lowest significant figure, right? But what if you're using a number or you're doing a calculation where you're not using their data, you're using your data, like what we're doing right now, right? What do you do in this case? So they're lenient here. You can do 2 or you can do 3, problem like. But in the previous question here, we were bound to use how much? 3. This is 3, this is 3, so my final answer had to be 3. Okay, so you cannot say they're lenient, don't worry about it, but on the question, be careful. Use the data in A to determine the radius of the orbit. So you need to find the radius of this stationary satellite around the Earth, and you have to use the data given in A, right? So can you try this? There's something very similar in your exam. So that's the power key. Oh, radius of Earth, 6.38 and 10 per 6. So this is an example of a question where you actually have to derive an equation to solve it. Okay, of the equations we have used so far, it wouldn't work. So you have to derive it. Now, what if you don't derive and you memorize that equation? It's fine. They will allow it. Do you know which equation I'm talking about? T square GM times R cubed. Okay, so let's do this. There are 3 marks here, and if I had this question in the exam, I would still derive it even if I knew it, because 3 marks is way too much to just use an equation. So how do we derive this? For anything undergoing circular motion, what was the criteria? The force centripetal is equal to what? The force gravitational, because circular motion has to be provided through an external force. Centripetal force is m omega square r, and gravitational force is g m by r square. That small mass cancels out, so eventually you get gm times r cubed equals to 1 by omega square, or no, sorry, gm equals to omega square r cubed. So we are trying to find what here? Radius. So you can use this here, and I'll tell you why deriving it is more fruitful in this particular scenario, because what are we trying to find here? Radius, right? And what have we found earlier? Omega. So if I use the derived formula, the one that we use more often, t square equals to 4 pi square by gm r cube, it'll actually not take you to the answer directly. You have to go back, because into t is provided, and what are we provided to right now? Omega. So wouldn't this be the better equation to use, right? So once you derive it, you might find that there's an intermediate step that's helpful for you. So what is g? 6.67 into 10 to the power minus 11 into what is the mass of Earth? 5.99 into 10 to the power 24 equals to, now I can use my omega here. So omega squared 7.27 into 10 to the power minus 5 squared into r cubed, right? So that's the radius of the satellite cube. So from here, you'll get the value of r. You got how much? 4. 10 to the power 7. Is that okay? So yeah, that's how you do this question. Okay, let's move on to the next one. We'll do a potential category. Look at this. An object is projected vertically upwards from the surface of a planet at fast enough speed. It can escape the planet's gravitational field. So what is this all about? Escape velocity, right? This means that the object can arrive at infinity where it's 0 kinetic energy. The speed at which the speed that is just enough for this to happen is known as the escape velocity. By equating the kinetic energy of an object at a planet's surface to the gain in the potential energy in going to infinite, show that the speed of escaping is given by this formula, where r is the radius. I think this is 1 and 2 total 3 marks. So how do you do this? They give you the direction by equating kinetic energy of the object, right, to the planets at the surface, to the total gain in the potential energy. So the way you do this is what we did earlier. Your object will go from the surface to where? Infinite, right? So this distance is radius of the Earth, and this is infinite. So what you need to do is you need to find the potential difference between the 2 points, right? So what is the potential at the radius of the Earth? What's the formula? Minus g m divided by radius of Earth. And what is the potential at infinite? Minus gm divided by a distance of infinite, which would be how much, by the way? 0, right? So if you go to a distance of infinite, that's 0. And this is going to be obviously minus gm by re. Now, I need to find the what between these 2 points, the potential difference. So my potential difference here is going to be 0 minus gm by re, right? So eventually, what should that be? Minus gm by re. So my potential difference is just going to be how much? Gm divided by re. Now, it says GP, like the potential energy. How does one get potential energy from potential into mass, right? So phi del phi into m, so into m. So that is my potential energy, and that's my GP basically. Okay. So in the exam, you can skip a couple of steps here. So you don't need to show this. You can directly get to that point, but I'm showing all the points that we need. Okay. So my change in GP for this mass is GMM divided by RE. Now, they said that this loss in GP would be converted to what? Or sorry, this gain in GP comes from where? A loss in KE, right? So therefore, you write down that KE lost must be equal to GP gained. What is KE lost going to be? Half mv square. And what is GP gain? GMM divided by radius of Earth, or just r, that's it. Okay. And you'll notice that one of the mass cancels out. We talked about this last class, which is very important, which says that the escape velocity is independent of mass. It doesn't depend on a particular mass. Every mass has the same escape velocity. And yes, once you rearrange this, I'm going to keep that with v, right? V squared. So v squared equals to 2gm divided by r. That's why I was looking at the marks. It looks a little undervalued. We did a lot of steps here to get to the answer. Okay, it says, hence show that v squared equals to 2rg, where g is the acceleration of free fall. Right, interesting. How can you convert the right-hand side to 2rg? Multiply by 1 by r. Separate r's.
G equals to Gm by R squared.
Yeah.
So that means on this side we just have Gm by R. But then if you multiply both sides by 1 by R.
Oh, both sides, that's what you meant? Or one side? So what you're supposed to do here is, I'll show you another technique. It's the same thing. You multiply by r, and you also what by r? Divide. Do you know that's completely fine? You can do that. Why? Because you're not doing any overall change to the equation. So as long as you multiply and divide by the same number, it's allowed, right? And once you do that, you can do something else here, which is 2gm into r divided by, what's the r into r? R square. And within this, there's something that is useful for us. What is that? Yeah, so there's this thing that you see here, gm by r squared. This gm by r squared is what? G. So therefore, v square equals to 2rg. Is that okay? I will do one more question. Wrap up quickly. I want to start a new topic. Now the poor one again. Are you done? Is it okay? Do you understand this part? Okay, let's see the next question. It's important. Okay, so let's see this question. Define gravitational potential. Let's write down the answer. What's gravitational potential? It's the amount of work done in bringing a unit point mass from infinity to a point in a gravitational field. Okay, so let me write that down. So you can see these students were lucky. They got a 5-mark bonus here. Things that you have studied before. So heads up in your whole paper, it's a 100-mark paper, right? You have around 15 questions, sometimes 14, sometimes 16. So 15 questions, it's almost like certain you'll have like a 3-mark definition to begin with, sometimes 5, sometimes maybe 1. It varies, but on average 3, right? So I know it sounds probably not true, but it is what it is. It's 15 into 3 is 45 marks, right? So there's 45 marks that you can just study and you'll go to the exam and you'll find the exact same thing being asked to you. Okay, nothing you need to apply, no analytical skills to apply, nothing to, think and write about. They'll just ask you definition, you just write the answer, right? So 45 marks is quite a lot given that you have A at 60. So A was 60 chilo. Sometimes it's 55, sometimes it's 62, right? So you get an A if you get 60 out of 100, right? So, you just need to get some 15 marks from 15 questions, which means you need to get 1 more mark from every question. Do you get my point? Other than the definition, mark from the entire question, telling that you can actually achieve 60. But yeah, I keep saying this, and students, they always do the same thing. They make mistakes in the definition itself. I don't know what happens. So because this is one thing you can actually study and go. The rest of them are up to the question, right? So this one, for example, define gravitational potential. I'll give you a list later on, 72 definitions. Maybe that's the problem, okay? I forgot to mention about that. But yeah, the thing is that 72 যদি memorize করে যেতে পারো, you are guaranteed at least 30 marks, right? Let's be conservative here. 30 marks to আসতে পারে, 2 marks করে যদি আসে. So yeah, what's gravitational potential? It is the depends on what B you have. 70. So that's 86%. A2. No, A2 to 86. So that is to convert grade paper A. $70 plus. No, A. For A star. Oh, depends on the A number. 86. That's 94. So 85 out of 100. No, that's given that I'm accounting for no scaling. Yeah. So if there's scaling there, probably you could maybe do 80 and get it, right? I have a student, yeah, or 90 or 90% paise, like, in marks, right? তারপর হচ্ছে paper is 89. If you do the math, it's 124 divided by 130 মনে ছিল, so into 100. I'm not sure কি হয়েছে, I have to check the paper again. So basically it was 90.15 or something, right? Or paper as 89. So ও এখন যে রিচেকে পাঠাবে নাকি রিচেকে পাঠায় তো এটা করার কিছু নাই না so I think you should just focus on A2 যদি এরকম কোনো সিনারিও থাকে there's no point sitting back and wondering কেন 90 আসে নাই just A2 তে do 92 and show them that you're capable so I think that's better okay হ্যাঁ যেতে পারো